Welcome everyone to our DinAmicI seminar. Our first speaker today is Elise Goujard from Nantes, and she will give us an introduction to dynamics of polygonal billiards. Thank you.
Thanks a lot. Thank you for the invitation. I'd like to present some results and some techniques about dynamics of polygonal billiards. And first, let me show you different billiards. So in the mathematical model of the billiard, we will consider only one ball, which is a point, which will move without friction on the table. And the only rule is that once you get to the side of the billiard table, the trajectory reflects with the same angle as the incident angle. Okay, so there is several shapes that you can study. And what is interesting is how the shape governs the dynamical behavior of the system, and for instance, the trajectories. So the first billiard table that you see is a scenario billiard. So it's a billiard in a square with a round obstacle in the middle. And to study such systems, you can use a lot of ergodic theory, etc. They are really chaotic, and you can use like a lot of interesting ergodic theory results to study this. This is a billiard in a very different shape. It's in the ellipse, and you see the trajectories are very regular. So here, to study this, you will more use like integrable systems, CAM theory, and so on, to get some information about the trajectories, for instance. Here below is the Viminovich Stadium billiard, which is very chaotic. And here you can use, for instance, spectral theory, more analysis to study this dynamical system. And here I will focus on polygonal billiards that seem a bit boring at first, because you see that the trajectories behave very regularly in a sense. Okay, but I will show you that it's in fact interesting, and that you can use a lot of geometry to study the dynamics in this billiard. So my point is that depending on the shape of the billiard, you want to use a different field of mathematics to study it. So it's really rich dynamical system. So I chose to present you 4 results about this family of billiards that I like. This is just my personal choice. There is a lot more, but this is 4 results that I find interesting. And they will be summarized by these 4 pictures. So let's begin with some result about ergodicity. Of course, this is a classical question to ask when you look at a dynamical system. So let's consider first the standard billiard table, which is the rectangle billiard table. It's quite easy to show that depending on the slope of initial slope of the trajectory, it will be either periodic if you throw the ball with a rational slope, or it will be dense and uniformly distributed if the slope is irrational. Okay, I will show you how to prove this result actually later. So you can ask, is that behavior similar for other polygons? So the first thing is no, it's not as simple as that. So here, if you take the L-shaped table, as in my first slide, this is an example of a non-periodic trajectory. So for that, you have to believe me, because I told you it's not periodic. But you can see, just looking at the picture, that it's non-dense trajectory, and certainly not uniformly distributed trajectory, right? So you can guess that it will never visit the corners in white, right? There is also examples, quite easy to construct, of dense trajectory that are not uniformly distributed. So here you just look at the trajectory in the rectangle with some vertical barrier in the middle. And I see, so you have to believe me that this trajectory is dense. But you can see by yourself that it spends more time on the left side than on the right side, right? I think the picture is pretty convincing. So a first result in the direction of this kind of behavior of trajectories is a result by Veitch in the 90s. It gives a sufficient condition on the shape of the polygon to get the dichotomy, either periodic or uniformly distributed tendons. And he construct also a family of examples of such billiards that such polygons that have this behavior for the trajectories, similar to what happened in the rectangle. So we come back to this example later. Let me move on to the second one. The second one is an infinite periodic billiard table with rectangular obstacles. And you play billiard in this table, in this infinite table. And here what you can look at is the diffusion rate of a trajectory. So what is the diffusion rate? Basically, you look at the diameter of the trajectory at time t. So it's inside a ball of radius something. And you look at how this diameter grows as t grows. And here in this case, it goes as t to some power, which is called the diffusion rate, which is 2/3 here. Okay, so this 2/3 at the time it was discovered was really surprising for at least physicists, because the usual diffusion rate for more standard dynamical systems are maybe 1 or 1/2, like square root of t. For instance, for the periodic senile billiard, you get square root of t, 1/2. But this 2/3, something in between, was very surprising at the time. So we'll come back to this number 2/3 later. Let me just mention that there is other result. So I just mentioned one, is that if you can play with the obstacles by adding some corners to get some funny diffusion rates, like this rational that goes to 1 as the number of corners goes to infinity, and etc. You can really change the shape of the corner and the obstacle side and get other results. So this family of models are called wind tree models because it's supposed to modelize the wind in the forest somehow. And I will come back to this later also. The third result that I want to present is a result about counting trajectories, special trajectories. So it's also in the L-shaped table that I pictured at the beginning. And here you can wonder, for instance, how many trajectories go from this corner to this corner, okay? So 2 corners of angle pi over 2. And you can, so of course it's easy to see that there is an infinite family of trajectories from going from this one to this one. But you can count them. You can count the one of bounded length as the length goes to infinity. And the first part of the result is that the number goes as L squared with some explicit factor, which is 1 over 2 pi times the area of the table. But this is not, I would say this is not very surprising. This is the same rate that you get in the rectangular table, for instance. Okay, so what is nice is that the constant is explicit. But the part that I find really nice is that if now you look at trajectories going from this corner to this corner of angle 3 pi over 3 over 2, now you get not 3 times more, but 4 times more trajectories asymptotically. And this 4, I never found a simple reason why it should be this number 4. Like, you could believe that this is a rather simple problem to address, but this number 4 is kind of mysterious just looking at the billiard. So I will come back to this number later also. And yeah, finally, the last problem that I want to present is the maybe famous illumination problem. So it is as follows. So you consider a billiard still in a polygon. Actually, here you have to also consider a billiard with a polygon with rational angles. And you ask the following questions. If you consider 2 points in this table, is there a billiard trajectory from the first one to the second one? Or if you fix a source, like this red one, can you be sure that it will reach any point in the billiard table via a billiard trajectory? And the answer to that problem was given in 2016 by Lelièvre-Monteil-Vaz. And the article is called "Everything is Illuminated," and it says what it says. So any point illuminates all the room, but finitely many points. There are actually examples of points that are not rich, like pair of points that are not linked by a billiard trajectory. If you consider this particular shape, there is no billiard trajectory between these 2 points. Okay, so this is an example due to Tokarski. And later, Wolecki showed that the number of pairs of points that do not eliminate each other is finite, actually. So this is even stronger. But what I want to emphasize in this result is the any point. So as you may know, it's a lot easier to show results like almost every point eliminates almost every other point. And this, I think, it was not formulated like this, but it was known before. And the result that any point illuminates all the room is due to a breakthrough result by Eskin Mirzakani Mohammadi that I will mention later. So this is really a strong result in this field. The fact that you are able to say something for any point in any rational polygonal chamber. Okay, so these are the 4 results that I wanted to emphasize. And now let me talk about how you do that, how you prove such things, etc. Oh, sorry, I forgot to mention a number question in the field, just to say that things are not that easy. So if you consider billiards with irrational angles, we know almost nothing. For instance, in a triangle, we don't know how to prove that there exists even one periodic trajectory. So in this triangle, which is acute, we actually do know one, which is the trajectory formed by the heights of the triangle, which is an old construction. But even in that case, we don't know if there exist other families of periodic trajectories. And if we consider triangle with obtuse angle, we don't know if there exists such a trajectory. So there was a computer-assisted proof by Rick Schwartz for triangles of angle less than 100 degrees. But this is how far, this is the only thing that we can get. This is the best result known so far for triangles. So yeah, the tools that I will present heavily use the fact that the polygons that I consider have rational angles. Here we do know how to deal with polygon with rational angles. So how do we do that? So let's consider the example of the rectangular table. And let's prove the first result, basically, that this dichotomy result. So how you do that? The only annoying thing about this system or this trajectory is the reflection along the sides. Okay, so this change of angle is really annoying. It's a discrete change. Okay, it's a bit annoying. But if you look at the trajectory in a reflected copy of the billiard table, so here I take the reflection along the sides. Here the trajectory just go straight in the reflected copy, right? And I can continue to do that forever. So once I reach this side, I can just continue in the reflected copy of the reflected copy, and it just goes straight. So I can just continue forever. And if I do that, I can prove the result that we have this dichotomy in the rectangle, right? So you have to think a little bit, but I'm sure now you have just the trick to prove this dichotomy. At least you can prove easily that if the slope is rational, then you get a periodic trajectory. But okay, this is for the rectangle that ties the plane, so everything is fine. But what about the other polygons? So in fact, so instead of just continue unfolding forever and forever, you can observe that the number of directions that the trajectory takes is just finite because the angles are rational. Here, in this case, the trajectory takes only 4 directions. So if you consider only 4 reflected copies, the other reflected copies are just translated copies of these 4 ones. Okay. So for instance, here, this copy is just a translated copy of this copy. It basically corresponds to the same direction in the original, the starting table. So you can just say, okay, I will just study the finite number of copies that I need, and the other copies are just translated copies. And doing that, you end up with a linear flow, a directional flow, in a new surface. So here it will be just the torus. But in general, it will be higher genus surfaces, for instance. And the only property is that they are constructed by polygons with sides identified by translation, because we have this property of having translated copy. And this has a name. I mean, this is the family of surfaces that we study when we look at the dynamics in these billiards. And it's called translation surface. So this is the example for the unfolding of this triangle, for instance. We get also the linear flow in some other genus 2 here, surface. So I will start by mentioning some facts about these translation surfaces and their moduli spaces that are useful to the study of the dynamics of billiards. So I hope I convince you that it's useful to study such objects and the directional flow in such objects, knowing that it makes sense to speak about, for instance, the north direction in such objects because the sides are just glued by translation, which will preserve this direction. And there is many ways to think of these objects. So you can just think as polygons glued by translation, but you can also see that they inherit from the plane of a flat metric, the Euclidean metric. So everywhere inside the polygon, you get just the Euclidean metric of the plane. Also along the sides, everything is fine. You see a piece of the plane. And you may have some conical singularities at the vertices of the polygon. So you get a flat surface with conical singularities. It happened that the conical angles are just multiples of 2 pi because of this translation atlas. Another way to think of this, if you wish, is just to take a Riemann surface with a holomorphic one form on it. It's totally equivalent to this definition. It may be useful in some cases to think of this object as Riemann surfaces with holomorphic one form. Okay, so you can get the genus of the surface by the Gauss-Bonnet formula. So here, if you do the exercise, you can see that there is one singularity of angle 6 pi. Therefore, the surface is genus 2. You also have foliation. In each direction, you get a foliation on your surface. For instance, a vertical foliation. Okay, so these are really rich geometric objects. And to get some properties on this object, it's fruitful to study their moduli space. So the family of all surfaces sharing the same combinatorics, meaning the same orders of conical singularities. Sorry, so you consider, for instance, the family of translation surfaces of genus G. So there is a relation by cutting and gluing. So you identified the patterns that are obtained from each other by cutting and gluing pieces. And inside this big moduli space, you can look at the subsets formed by surfaces that have given singular conical angles. Okay. Why we care about this space? So it is in these spaces that there will be some dynamics that is relevant to the dynamics of billiards. And also we know quite much about these moduli spaces when we fix the conical singularities. So we have a nice system of local coordinates on this space, this family, which is just described by the sides of the polygon. On your pattern, you just look at the size of your polygons as complex numbers, and it gives you local coordinates around this point on the family. So here, for genus 2 surfaces with one singularity of angle 6 pi, for instance, the space is locally shaped as c to the 4, and the 4 complex numbers that are relevant are these 4 complex numbers here. So here I just show an example of a surface which is close to, so a point in the family, which is close to this one, okay, because it has close by coordinates. So we have a nice system of local coordinates, and we have actually, so a nice structure. So the whole family is a complex orbifold of dimension 2g plus the number of singularities minus 1. There is a nice action of this on this family by SL2R. And what is this action? You just act on the polygon by SL2R, like in the natural way. So you act on each vector defining the polygon by a matrix of SL2R. And it preserves the singularity data. So you land in the same family of translation surfaces. You have a nice measure, so you will be able to do some ergodic theory. The nice measure is just Lebesgue measure in local coordinates. It's SL2R invariant on the moduli space. And actually, there is a result of Mazur and Rich that says that if you restrict to surfaces of bounded area, the measure is finite. Okay, so you can induce a finite measure on the subset of the moduli space. So you have all the ingredients to do some nice dynamics. So let me go now to the tools. So how we study these systems. So the one important tool that we use is some renormalization. So let me try to give some idea of what it is in this case. So the vague idea is that if you want to study the linear flow in some fixed translation surface, it is related in a sense to the dynamics of some flow in the moduli space. So in the family of all surfaces sharing the same singularity data. What is this geodesic flow? So I presented the action of SL2R. So if you restrict to the matrices of this shape, diagonal matrices of these shapes, it is called the geodesic flow for a good reason. It is really the geodesic flow for the Teichmüller metric, which is something that I won't talk about. So there is a nice metric on this set. And Teichmüller theory basically gives you that the geodesic flow is just the action of this matrix on the moduli space. But why do we have such a relation between these two flows? The linear flow in some fixed individual surface and the geodesic flow on the family. So let's, I will try to show you why we get this relation. But first, actually, it's not really on the whole moduli space maybe that I want to look at. Since I look at a subgroup of SL2R, it's natural to just consider the SL2R orbit closure. Okay, and I will tell you a bit the difference in a moment. Okay. So what is the idea? So you want to study a linear flow in a fixed translation surface. So up to applying some rotation, let's say that this is the vertical flow, actually. So you have the vertical flow in some translation surface, and you want maybe to study a very long trajectory. If you look at the action of GT, the geodesic flow, what it does is that it takes the horizontal direction and it stretches it, okay? And the vertical direction is squeezes. So actually, after applying this geodesic flow, maybe you get a very short vertical trajectory. I mean, if you apply this geodesic flow. Okay, but the surface looks very different. So actually, there is a result about the dynamics of this geodesic flow. It is actually ergodic. So it means that you can, so it's recurrent and you can get arbitrarily close to the starting surface in your moduli space after some time. So it means that up to some cutting and gluing, this new surface, you can get close to the first one. So your very long trajectory in the first one is transformed to a shorter, as short as you want trajectory in a surface which is arbitrarily close to the first one. So this is why there is some relation between the two flows. So in practice, this relation is encoded by some discrete dynamical system. So when you look at the vertical flow in some translation surface, you can encode it in a interval exchange transformation, looking at the first written map. So you take any horizontal, I mean, not really any, but there is some construction of horizontal segments where the first written map of the translation flow gives you an interval exchange. Okay, so I tried to picture that on this. I think Magali will go back to this later. And let me just say that there is an induction on this interval exchange that encode in a way the action of the geodesic flow on the moduli space. So this is how we use renormalization in practice. So let me mention some consequences of this principle. The first important result is that is Mazur's criterion that tells you that if you look at the trajectory of the geodesic flow in the family, if it does not diverge to infinity, it means that there exists a compact such that it goes back to this compact infinitely often. Then you know that the vertical flow on your starting point, like your fixed surface, is uniquely ergodic. So the behavior of the trajectory of the geodesic flow on the moduli space is linked to the trajectory of the vertical flow on your fixed surface. So this is the first instance of this principle. And the Witch dichotomy is actually also an example of this principle. So what it says, so I just mentioned it at the beginning, but the precise result is as follows. If one translation surface, a fixed translation surface, has a closed SL2R orbit, then you have this dichotomy. So the linear flow in any direction is either completely periodic or uniquely ergodic. The same dichotomy that you get in the rectangle. And it also gives a family of examples. So for instance, all surfaces constructed from squares, you glue several squares together by translation. They satisfy this condition. It's pretty natural. And we also know that the surfaces that have a closed SL2R orbit are the one such that the stabilizer for the action of SL2R is a lattice in SL2R. So you can study them that way. It's not an equivalence, actually. So this is actually, which dichotomy is just an example of this renormalization principle, like the link between the orbit in the moduli space by the geodesic flow or the SL2 action, and the linear flow in the fixed translation surface. So here, it's quite important to understand what are the SL2R orbits. And the first thing is that if you consider a generic point for the natural measure on the moduli space, its SL2R orbit will be dense in the whole moduli space. Okay, so generic points have dense orbits. That is very good, but when you do dynamics in polygonal billiards and you do this unfolding, you end up with a specific surface, a fixed surface, which is maybe not generic. Actually, it's almost never generic because it has a lot of symmetries due to the construction. So you don't know anything about the SL2R. I mean, this result does not say anything about billiards so far. But recently there was this important result by Eskin Merzakani Mohammadi in 2015, saying that now take any surface, really any surface, not almost every, you can say things about its SL2R orbit closure. And what you can say is that it's a linear submanifold in the moduli space, meaning that it's locally modeled by, it's cut out by linear equations with real coefficients in local coordinates. So basically it behaves as the whole moduli space itself, sorry. There are actually also quasi-projective algebraic varieties by a result of Philippe. So the conclusion is that the SL2R orbit closure are very nice, and you can do a lot of things that you do on the moduli space on SL2R orbit closures. And an example of an application of this result is the illumination result that I presented at the beginning. Okay, so just to recap this principle of renormalization, when you want to study the billiard flow in some rational polygonal billiard, you can unfold it to a linear flow on the translation surface. And now you can, by renormalization, get information by studying the geodesic flow on the orbit closure of this fixed surface on the moduli space. Now I want to finish by mentioning what are these 4 2/3 that I mentioned at the beginning. So they are related to this dynamics on the moduli space, actually. So the first invariants for the SL2R action that you can get on the moduli space are the so-called Lyapunov exponents that give the mean eigenvalues of the monodromy. I won't define it precisely, but basically you follow the absolute homology along the geodesic flow, and you look how you look at the monodromy of this co-cycle, basically. And the mean eigenvalues gives you Lyapunov exponents. And the 2/3 that was the diffusion rate for the the classical ring tree model, is some Lyapunov exponents of some moduli space obtained from your billiard. There are also other invariants on the moduli space that are called Ziegelwitsch constants, that are responsible for the count of closed geodesics on surfaces. So actually you can show that the number of closed geodesics or geodesics coming starting from one singularity and ending up at one other singularity. The number of such closed geodesics of lengths bounded by L goes as L squared with some constant in front, and the constant is called Ziegelwitsch constant. It's in the same for almost every surface in the moduli space. So it can be computed looking at the moduli space. And these four, the ratio of trajectories for the L-shaped billiard table is some Ziegelwitsch constant for a related translation surface. And finally, I said that in these moduli spaces, there is a natural measure, which is finite if you restrict to some subset. So you can speak of volume of these moduli spaces, and they are just numbers. They are actually rational multiple of powers of pi. And all these three families of invariants are related somehow. So the sum of Lyapunov exponent is related to Ziegelwitsch constants by the formula of Eskin, Kontsevich-Zorich. And there is also a relation between Ziegelwitsch constants and volume of strata by Eskin, Mazur-Zorich, and Mazur-Zorich. So basically, if you, for instance, have volumes, you can get Ziegelwitsch constants, and maybe you can get information about Lyapunov exponents. At least there's some, which is in some cases sufficient. For instance, this 2/3 was just obtained because we know that the sum is equal to something. The first one is equal to 1. So we get the second one is equal to 2/3. Okay, so this is all I wanted to say about this quantitative invariant of the dynamics that gives information on billiards. And let me just mention in a few minutes what is done now in the field. So it may be closer to what I do. So maybe I forgot some directions because I'm more interested in some personal direction, but okay, let me say some words. So what you can do next is to understand more the topology of the moduli space. We know very few about the topology. We know that there is maybe several connected components. So the connected components are classified, but that's almost it. So now, recently there was a nice compactification constructed for these moduli spaces that allowed to compute Euler characteristic and some Chern classes of these moduli spaces, as well as the Kodaira dimension. But this is all the information that we have on the topology of this space. And it's important to have some information because like it's related to the dynamics of the geodesic flow. There are also now some algebraic approaches developed to compute these invariants that I mentioned before, like Lyapunov exponents or Ziegelwitsch constants or volume, etc. There is works by Schellmüller, Sauvaget, Zaghi, etc. recent works expressing this invariance as Hodge integrals, for instance, on the moduli space. There is a direction, an important direction of classifying the SL2R orbit closures. So it's I hope that you see now that it's very important for the dynamics of billiards, for instance. So we don't know much also about the orbit closure classification. It's done in genus 2. We also have a lot of results about Teschmuller curves. And the higher dimension orbit closures, there are some finiteness results about them. But there is just very few examples of higher dimension closed orbits by the SL2R. And for instance, this example is constructed from unfolding a quadrilateral, for instance. So you can also go the other way around. You can use billiards to get some result about more like result on moduli spaces. There is also a big question about how to compute individual Lyapunov exponents. For instance, it's not shown, as far as I know, that they are rational, so it's conjecture. We know that the sum is rational. We know plenty of examples where they are rational, but it's not shown in full generality. And how to compute them, it's a big question. So what we do know is that the Lyapunov spectrum is simple by Avila-Viana. There is this explicit formula for the sum, asking continuous range. We know cases in what cases there are 0 Lyapunov exponents. There is some lower bounds for partial sums, etc. But this is the only thing we know. One can also study this invariance and other dynamical properties for surfaces of large genus. This is a big part of what I do also. So you can look at infinite type translation surfaces. For instance, the one you get when you unfold an irrational polygon. So you get translation surfaces of infinite area. So there is a nice development about these infinite type translation surfaces, but we don't know much so far. So for instance, classifying the type of singularities that arise on such surfaces is already very hard. Let me skip this point. So there is plenty of other models that generalize this translation surface case, like affine surfaces, for instance, that are studied now, and etc., etc. So I think I will stop there. Thank you for your attention.
Thank you very much. Do we have questions for Elise? Sorry, I don't know if it's simple, but can you just say a few words of how, from the result of Eskimi-Zakani-Mohammadi, you deduce the illumination? I don't know if it's...
So I don't think I can say it in a few words, but basically you write. So you look at the set of points that are not illuminated, and so the illumination property, like the fact that 2 points illuminate each other, is SL2R invariant, right?
Mm-hmm.
So the set of so if you formulate the things right, I don't remember exactly how it did this, but you can look at some set, maybe the set of. I think you have to look at some product set. Okay, so you have to construct some set from this situation, which is SL2R invariant,
Mm-hmm.
and their result maybe you get, sorry, I forgot the details, but in their results, you can get some finiteness results of, yeah. I don't remember exactly how it works. I've looked at this, but yeah, you have to work a little bit. I mean, it's a whole article of Lelièvre Weiss, but basically it uses this SL2R invariance of the illumination puppet. Yeah.
And there are quantitative bounds on the number of points that are not illuminated.
This is a good question, and I have not checked. So I don't know so far. So it's sure that the result of Eskin-Mirzakhani is not constructive, so it just gives some finiteness, but so yeah, I have not checked, sorry. So probably in some very specific case, it's possible to do that. Probably some lower bounds are also, some bounds maybe, yeah, exist, but I have not checked if that is done yet, sorry.
Okay, thanks. Other questions?
Maybe I have one. May I?
Yeah.
Thank you for the presentation. Going back to the one of the first of the four results that you presented, where you introduced the dichotomy in the rectangle, and then you showed that in the L-shaped. Yes, this one. Thank you. And what, like, if it is meaningful as a question, what happens if the L shape is the L shape can be seen as a bigger square and a smaller square on the bottom right? What happens if the smaller gets small and small and small, and the L shape degenerates to the rectangle? What happens with respect to the non-periodicity and non-density, or the density and not uniformly distribution of trajectory? If it makes sense.
Yeah, it does make sense. And so we do, I think for the moment, we do know how to treat such limits, because so the moduli spaces of the L-shaped table and the moduli space of the rectangle are like two whole different moduli spaces. So I mean, we have, yeah, I should say there is something developed now to look at boundary of such moduli space, etc. But I don't think that we have enough tools now to. Maybe I should be corrected. Maybe someone in the audience can correct me, but I don't think there is enough tools now to look at such limits. So yeah, you have to. Your intuition tells you something, but I don't know if we know how to prove that. So, yeah. So what I just want to say is that if the corner is really, really small, still you get the same behavior. It's really the same behavior you have in the same stratum. But it's, yeah, there is a gap between a small hole and nothing. Yeah. But
yes.
Yeah.
Thank you.
Other questions? Okay, if not, let's thank Elise again.
Thank you.
And we have a short break. So our second speaker today is Magali Jay from Max Planck Institute in Leipzig, and she will tell us about tiling billiards in the wind tree model. Thank you.
Yes, thank you for the introduction and the invitation. So I will talk about billiards, but a new type of billiards. So I will explain you that. I will introduce them and a few other dynamical systems. And then I will consider, I will study kind of a mix of all these dynamical systems and present you a sketch of the proof, which will use not translation surfaces, but half translation surfaces, which are almost translation surfaces. Okay, so tiling billiards are dynamical systems where the trajectory are in the plane, in the Euclidean plane. We take a tiling of the plane, a polygonal tiling, and the trajectories are in straight line in each tile of this tiling, and they are refracted when they cross a side, like this. So for a square tiling, this is kind of boring. You only have two types of trajectories, like the periodic one, which are 4 periodic, and the zigzagging one, like that. And this is all what you can get. But for other shapes, then you can have lots of different behaviors. So this is really an interesting dynamical system. And so this was motivated by the conception, the discovery conception, I don't know what, yeah, of metamaterials with index of refraction, with negative index of refraction. So you know that the light, when the light goes from the water to the air or from any material to another one, it is refracted. But usually the refraction index or indices are positive. And here for these metamaterials, the refraction index is negative. And so in our case, it corresponds to negative index, like the ratio between the two indices is -1. So you're really refracted as a mirror. Okay. So the questions we ask are the following. So what can we say about the trajectories? Are they periodic? Are they bounded? If they are unbounded, are they recurrent? Or do they escape to infinity? And if so, can we say something about the way they are escaping? And are they stable? If we change, for example, the rectangle into the square, sorry, into a rectangle or into a quadrilateral, do we have still the same behaviors? Or if we change, we keep the same tiling and we change the initial point, the initial direction, do we still have the same thing or not? Okay, so this was the definition of the tiling billiard. And one case that has been studied is the triangle tiling billiard. So you choose any triangle, for example, this blue triangle, and you rotate it, you rotate it by half a turn, you get the orange triangle, and then together they form a quadrilateral. And with this quadrilateral, you can tile the plane and play the tiling billiard in this plane. And the result is the following, is that for any triangle, for almost every initial direction, the trajectory is either periodic, like that, or linearly escaping. So you have a direction, and the nth step is approximately n times the direction. The error is bounded. Okay. So I haven't said, but if you have any question, please ask. So yeah, this was the triangle tiling billiard. And now I want to tell you a bit about the wind tree model. So Elise already talked about it. It was introduced to study gas so by Paul and Tatyana Ehrenfest. And yeah, so we have a small particle bouncing against big obstacles, which are here rectangles. And so it is reflected when it bounces. And again, we want to understand the trajectories. So first result about this dynamical system is that for every A and B, so every size of the rectangle, for almost every initial direction and initial point, the trajectory is recurrent. So we come back close to the initial point. And as Elise mentioned, we know also the diffusion rate of these trajectories. So at a time t, we are approximately at a distance t to the 2/3. So this is a lim sup. And actually, this result is also true when we take the mean along the trajectory. So this was a lim sup, and now we are averaging over all the trajectory. So we can really expect at time t to be at a distance t to the 2/3. But this is not always true, of course, because the trajectory is recurrent. Okay, so this was our second, so the second dynamical system that I wanted to present. And now I want to talk about Eaton lenses. So they are again motivated by physics. They are spherical ball of glass, but with an index, a refraction index, which varies depending on the radius. And it varies in such a way that when a ray comes in the sphere, it is really refracted, and it comes back. It goes out of the sphere in a point which is opposite, like here in the opposite direction and in the opposite point. Okay. And now we take again a periodic array of this sphere, and we shoot a laser and we shoot a laser ray in this array, and we want to know what is the trajectory. And so, okay, of course, we ask the spheres to be disjoint, and in this case, if they are disjoint, then for almost every admissible pair of the lattice in which we place the sphere and the radius of the sphere, there exists a constant c, which is a width, and theta, which is a direction, such that every vertical light ray in our system is trapped in an infinite band of width c and direction theta. So this result is holds for almost every admissible pair, and in fact, this is also true for every admissible pair and for almost every direction. Okay, so in the first statement, we assume the initial ray to be vertical because it doesn't matter. We can just turn the system. And in the second theorem, since the system is fixed, then we have to say almost every direction. This is not every trajectory like that, but every admissible pair for almost every initial direction, there is a strip in which the trajectories are bound are trapped. Okay, and now tiling billiard, the tiling billiard in the Wintry model. So I'm coming back to the rule of refraction of the tiling billiard. And as in the Wintry model or the Eaton lenses, I'm taking a lattice in the plane and I'm arranging obstacles in the plane. So lambda is the lattice and A and B are the size of my obstacles. And this angle eta is the angle here between the obstacle and the horizontal. Okay, so they are the parameters of my system. And I start with a vertical initial trajectory. I reach an obstacle, and so the trajectory is refracted inside the obstacle, as in the tiling billiard. And again, it goes out. So we can follow like that the trajectory. So you can see that we have some part of the behavior reminding us the Eaton lenses, because if I come back here, so this part of the slit, the trajectory is like turning around the corner as the light was turning around the center of the sphere for the Eaton lenses. So we have this part of the behavior which remind us the Eaton lenses, but we also have this first behavior where the trajectory crosses the obstacle and is so translated. So again, I will choose my parameters so that the obstacles are disjoint. And I showed that for almost every admissible parameters, there exists again a width c and an angle theta, such that every trajectory, vertical trajectory in this tiling billiard in the Wintry model is trapped in an infinite band of width c and direction theta. So we can see an illustration of the result here. So we really see the strip and the direction and the width. Okay, so how can I show that? So to prove this theorem, I use half translation surfaces. They are a bit like translation surfaces, but so the difference is that, so maybe you, so Elise told us that we can see translation surfaces as polygons with parallel sides glued, identified together. And here we allowed a new way of identification. That is, we can also use a rotation like that, half rotation. So for example, in this square, we don't identify the top and the bottom side as for the torus. We identify the top side both halves of the top side together and the both halves of the bottom side together, and we get a sphere, a topological sphere. Yeah. Okay, so this is a half translation surface. And as for translation surfaces, we can study their moduli space, the singularities of the half translation surfaces have conical angle which are multiple of pi. So we can have either pi, like in this case, in the middle of the top and bottom side. So here we have an angle pi, here as well, here also, and here also. So we have 4 singularities of conical angle pi, but in other surfaces we can have more angle, like 3 pi, 4 pi, etc. Okay, and so we do not Q the moduli space of this half translation surface. This is for quadratic, because we can also see this half translation surfaces as quadratic differential on Riemannian surfaces. And here I wrote -1 to the 4 to say that there are 4 points with a defect of pi, with a conical angle pi instead of 2 pi in the flat case. Okay, so now I will use these surfaces to answer my problem, to show the theorem. So the strategy is the following. I have the tiling billiard in the wind tree model. I associated to it a half translation surface, where the trajectory of the tiling billiard in the wind tree model becomes a geodesic. To study this geodesic, I use the renormalization trick. So I study the surface in the moduli space. I act with the geodesic flow in the moduli space, and then I come back to my initial problem. Okay, so what is this associated half translation surface? The first thing natural to do is to quotient by the lattice, since we have a periodic setting. So I have now a torus with an obstacle and a broken trajectory on a torus. The second remark I want to do is that I have 3 ways to cross, and only three ways to cross the obstacle. Either I am turning around a corner, like for the blue, light blue and black and deep blue trajectories. So the bottom corner or the top corner, turning around, or I am crossing the obstacle. And this is the only possibilities. So instead of having this obstacle and broken lines, I can just remove the obstacle and put a slit. So I have my torus, I forgot the obstacle, and I cut in the diagonal of the obstacle. So this remains in the obstacle. And I do identification from the bottom part of the slit to the top part of the slit, according to this these trajectories. So I have a yellow orange part here corresponding to the translation part, and blue part where the 2 halves are identified as in half translation surfaces. So this is not a translation surface, this is really a half translation surface. And we can, so I hope you can see. So here is, this is a paper. So I've done a slit here. And so maybe the colors are hard to see, but I have this yellow part, which I do like that. And I have my two blue parts here. And you can see that I have still a torus because I've done something in the middle, but the identification are outside of are the same. So I have still a topological torus with 4 singularities. So this is here. I have 2 singularities of angle pi here, this corner in the middle of the blue segment, and 2 singularities of angle 3 pi here. 1, 2, and 3. Okay. So I am in this strata, this stratum with 2 angles excess pi and 2 angles which less 1 pi less than in the Euclidean setting. Okay, and in this 2 torus, the first torus with the obstacle and the torus with the slide, with the slit, if we look at the trajectory outside of the rectangle, they are the same. Of course, I've done the slits so that they are the same. So like that, and if we take a longer trajectory, it's not the same. And so now the question I want to ask is how many times I'm crossing this trajectory is intersecting these 2 curves, because this will allow me to answer my problem. I need this information to know where I am in the plane. So here I have quotiented in the torus, but if I want to know where I am in the plane, I have to know how many times I intersect. So this is an algebraic number, h and v. So for example, if I know that after a time t, I've intersected the intersection number with h is -1 and with v it's 0, it means that I've started in this fundamental domain and then I'm here, just under in the plane. And if I can show that for any time I have the intersection number between the trajectory and h, for example, is bounded, it means that the trajectory is trapped in a strip in direction h. And of course, in general, it won't be h, it will be a linear combination of v and h, but I want to find a direction such that the intersection number between the trajectory and this curve is bounded. Okay, so to find this, so I have an intersection number to count, and the trajectory is very long, so it's possibly a big number. So I will use the renormalization trick. I follow the geodesic flow, and the trajectory is shorter. Okay, like until there, the intersection number is the same, so I've done nothing, but now I can cut and paste this extended square or parallelogram. Okay, so I cut and paste, and I get this, which is close to the first torus. So this is because the geodesic flow, as Elise said, is recurrent in the moduli space. So I know that for a generic surface, I will come back close to where I was in the beginning. And now since I have a shorter trajectory, I know that the intersection number will be much less. But I have to understand the link between these new curves, h prime and v prime, with h and v, the first ones. Okay, and this link, this relation is given by the Kontsevich-Zorich cocycle, a discrete version of the Kontsevich-Zorich cocycle, which gives me, this is basically a change of basis matrix, which express H prime and V prime, which express H and V in the new basis H prime and V prime. Okay, so now when I have an intersection number with H prime and V prime, I can compute the intersection number with H and V and vice versa. Okay. So I want to know how this matrix grows when the time goes to infinity, and I want to find a bounded direction, a direction where when I apply this matrix, the direction stay bounded. Okay. So, and this will be possible with the oscillated theorem. Okay, so I have, I recall I have my trajectory in the half translation surface. I have a long trajectory. It starts at a point, it ends at another point, and I want to compute an intersection number, so it has to be an homology class. So I close this trajectory to get a loop. And now there is something I have to be careful about. This is because I've stretched, so I apply the geodesic flow. So I stretch in one direction and shrink in the other direction. So it's nice because I shrink in the direction of the trajectory, but in the other direction, I'm stretching it. So this means that the maybe small path that I have added to close the loop will be stretched. So if I'm going far in the future, of course, in the direction of the flow, it will be, of the trajectory, it will be very short, but I will have a long trajectory in the other direction. So I have to be careful and to decompose my loop into several loops, and I will look at each loop in a different time scale. So gamma n is a loop where I can apply the geodesic flow for a long time, and I can assure that the horizontal component that I have added is small enough so that it won't be a problem. And gamma n-1 is such that I can apply the flow, but to a nearest future, and so on. And now, so I have of loops, and I can compute each intersection number in the right time scale thing. So at each time scale corresponds to a point where the surface comes back near the initial surface. So I can compare the two. And so I have a sum, which is here. And for now, W is any homology class. And I want to find an homology class which is contracted, such that this sum will be a geometric sum and converging geometrical sum. Okay, so I don't have much time left, but I will try to be quick. So I will use the oscillated theorem to find this contracted direction. So this oscillated theorem is a multiplicative version of the ergodic theorem, where we say that the space average, sorry, the time average converges to the space average. And here we are looking at cocycle. So it will be the Kontsevich-Zorich cocycle in our case. X is the strata, so Q -1, -1, 1, 1. Phi is the geodesic flow, and mu is Majorvich measure. So the cocycle is the Kontsevich-Zorich cocycle. We know that it's the flow is ergodic. We have that this is log integrable by a result of Forni. And so Osseledeth theorem gives us Lyapunov exponents. Okay, so it gives us growth. And in our case, since this E-ax is the homology group, we are on a torus. This is the absolute homology group. It has dimension 2. So we have 2 Lyapunov exponents. In this case, they are opposites. So and we know that they are distinct. So we have one positive Lyapunov exponent, one negative Lyapunov exponent, and we are interested in the negative part, the one which will be contracted. And so this theorem tells us that it exists, this direction we were looking for. This is the direction in the contracted direction. Okay, so we found this direction, but last thing I have to say is that here the theorem is for mu almost every x, meaning for almost every surface. But the surfaces I'm caring about, these surfaces here, they are very specific. I can parameter them with 7 real parameters, and I am in a space of real dimension 8. So they are not generic. A priori, they could be all non-generic, and I would be able to say nothing. But the nice thing is that I can, so if I have an open set of surfaces I care about, I can thicken it in the stable direction, which means that in each kind of fiber, not fiber, but each string I will put in the other direction of my open set, all surfaces will be either generic, like they will either be all generic or all non-generic. So when I thicken that, this open set for my surfaces, I get an open set in the moduli space, and I know that this open set for my surfaces cannot be, the surfaces there cannot be all non-generic, because otherwise it would mean that in the thickened open set, they are also all non-generic, and this is not possible because in the moduli space, there almost every surfaces are generic. Okay, so I'm relieved. I can apply Osseledeth theorem. I have a direction which is contracted, and this direction gives me the direction of the strip. Okay, and yeah, I can meet the trajectory. Can intersect this direction only a bounded number of times, which means that this direction is the strip in which the trajectory is trapped in the plane. Okay, and I will end there. Thank you very much.
Thank you. Do we have questions for Magali? So you know that your trajectory is trapped.
Mhm.
Does it also mean that the average distance is increasing linearly with time, or because in the
No,
picture
so
there was some.
yeah, it will go back and forth, and it should be recurrent also. So I've not written that, so I haven't talked about that, but I expect it to be recurrent. I mean, it's more than expected. I checked that, but okay. So it's recurrent, but for example, I don't know if I will go in, the trajectory will go in both direction. And I also don't know how much it feel the strip. So it's
And the
not
diffusion
a
rate,
linear, it's not a linear escaping. It will go back and forth. The other Lyapunov exponent should give us the growth rate in the other direction. And that's what I can say. I cannot say how much it feels the strip. Yes.
so and then sorry, that diffusion rate, we don't know explicitly what it is.
Yeah, so in this case, I think it's also, I can check, it's also 2/3.
Okay.
The same 2/3. We are not in the same stratum, but it's still 2/3. Okay, and so we can compute that, as Elise said, thanks to this formula with the sum, and since here we don't have that much Lyapunov exponents, it's easy to compute once we have the formula. So I can say explicitly that this is 2/3.
And can you have other shapes like the ones in the previous talk with more?
Yeah, so this we could do that also, and so basically everything would work the same way. We would have another slit, and we can easily compute the combinatoric of the slit. So this would not be a problem. Where there could be a problem is that we must check that the surfaces are generic. And so in this case, it was nice because I was missing just one dimension and I could extend in the stable direction. But in general, for another shape, for another slit, maybe I'm missing a much more dimension, and I cannot extend just in the stable directions. And then I'm kind of stuck and I can't say, I mean, I have to find something else. I cannot apply the same proof.
Thank you. Questions? Okay, if not, let's thank Magali and Elise again for the excellent talks.